Hi everybody, welcome to the NASA SEES 2023 High Altitude Eclipse Payload Team presentation. We're so thankful to have you guys here to listen to our project and to what we have done with our research.
Hello, I'm Alexander Boeckmann and I'm from Indianapolis, Indiana.
Hi, my name is Brochu and I'm from Mobile, Alabama.
I'm Briant DeJesus and I'm from Bronx, New York.
Hey, I'm Jorge Hernandez and I'm from Bronzeville, Texas.
Hi everybody, my name is Mendez and I'm from Caldwell, Idaho.
Hi, my name is Reveles and I'm from Richmond, Virginia.
My name is Schaeffer and I am from Philadelphia, Pennsylvania.
And I'm Sinha, I'm from Houston, Texas, and I'd like to extend a thank you to Professor Nokes and Melissa Pore for their guidance and help during this project.
For the NASA SEES intern project, we were given the NEBP. NEBP is the Nationwide Eclipse Ballooning Project. This project included high altitude ballooning, which recorded atmospheric data. In terms of high altitude ballooning, there's been a huge increase in studies. As you see on the graph on the right, we see how eclipse ballooning studies has increased from 1850 to 2000s. A study from the Royal Society of Publishing Records has also shown how temperature is affected by solar eclipse.
Another form of data was from the National Library of Medicine, who recorded increased wind speeds in 2009 eclipse in South Korea. And while there has obviously been lots of data collected during eclipses, high altitude ballooning data is actually quite rare. In the last eclipse in 2017, they collected high altitude ballooning data in Carbondale, Illinois. However, this was very minimal, and in the 2023 and 2024 eclipses, we'll be trying to collect far more data about the upper atmosphere.
Obviously, with these experiments and research, it is highly important to ask ourselves, why are we doing this and the significance? Obviously, we've already talked about this, but it's highly important to understand how our stratosphere and our atmosphere reacts to different variables, this being solar and annual eclipses. We need to learn more about Earth's atmosphere and how it can change depending on climate change or any other experiences. It is also highly important to expand knowledge on researching and on the atmosphere, as well as give opportunities to lower income communities so they can also create similar research projects like this one.
We did have to do prior research before starting this project. The NASA SEES program gave us different modules so that we could learn about climate change, space exploration, and NASA technology. We also got more specialized modules that talked a lot more about wiring, forming the balloon, and actually launching the balloon.
So for our mission objectives, our first mission objective was to create a functional balloon for the annual and total solar eclipses. We were going to record temperature, humidity, pressure, and camera data. Our second objective was to perform a tethered launch before the eclipse. Our third was to analyze atmospheric data for a better understanding of the eclipse's effect on the atmosphere. And the fourth was to complete a research paper on the atmospheric effects of eclipses.
Here we have a Gantt chart that kept us on track and organized about our tasks and what days they needed to be completed.
Before we began assembling, we divided into groups of two. These groups resulted in Raspberry Pi and Arduino.
So we had to settle on, we were given a Raspberry Pi and Arduino. We had to pick which one we wanted to use. We ended up going with the Raspberry Pi because all of our sensors were compatible with both, but our camera was only compatible with the Raspberry Pi, and pin mappings were also a lot easier to find on the Raspberry Pi.
The next thing we had to consider were sensors. And with this, there are a lot of constraints that we have to keep in mind to ensure that we're receiving accurate data, like extreme atmospheric conditions such as temperature and low pressure.
So we settled on the BME 280 because it's lightweight, accurate, versatile, and it measures all our atmospheric conditions like temperature, humidity, and pressure. And based on pressure, we calculate the altitude that our balloon is flying at.
Because we'll be flying during an eclipse, we'd like to receive visual data. And to do this, we had a couple options like the ArduCam Module 3, PiCam Module 2 and 3, and infrared cameras to choose from.
And all of these different cameras had very specific coding, which we were able to achieve, like an initial start and a possible reboot, as well as a code for automatic lens fixation.
When designing our box, there is different things that we have to keep in mind. The requirements of the box were a 12-pound limit, a camera, temperature sensor, humidity sensor, air pressure sensor, GPS, battery. And on the right, you're able to see a digital drawing that we use to map out how we want to design our box. Actually, this is the box that we use itself, where we actually put in the Raspberry Pi and everything that we needed.
So with box assembly, we used foam boards in order to make our payload. So we used two 6x6s, two 4x4s, and two 4x6s. Our first problem was if we were either going to use hot glue or super glue. We did a weight test where we basically glued 2 boards down, and then we saw how many newtons it took to break it, and super glue won. So that's what we used.
Testing and launching. Through this project, we are testing sensor calibration, indoor controlled drop tests, weight tests, final launch tests, and the weight tests on different adhesives.
Of course, we also have things to consider before launching, such as the time of day, the weather, the wind speed and direction, the launch date, and of course obstacles such as trees.
Before launch, we considered the following. We weighed our payload, measured the string, weighed the string, and filled our 24-inch balloons with helium. Then we did a neutral buoyancy test, which was where we took the mass of the payload and made a bag with coins weigh the same amount, and so we attached the balloons. And so basically we wanted it to be where it wasn't going up too high and it wasn't sinking to the ground. So it was just staying in the same spot.
So we first began our experiment by making a drop test, in where we basically simulated a weather balloon launch, but in a more controlled and a descending manner. We basically used our payload box and wrapped a string around it. We went up to the 4th floor of a tall building and we took it down. The entire thing took around 4 to 3 minutes, and we were able to gather some data.
We did this because we needed to calibrate our pressure to altitude system. Because we didn't have a specific sensor for altitude, we needed to convert from pressure to altitude. So as we were dropping it down, we were collecting the data, which we were then processing to give us a raw altitude.
After our drop test, we were able to plan our launch. We spent the last day working on the final tethered launch, where we debugged the microcontrollers, sensors, and cameras, assembled the box, attached the box and the microcontrollers to the 7 balloons, and sent the balloon into the air using a kite reel and brought it back down to collect its data. Here is our balloon on one of our launches. As you can see, it's a collaborative effort with everybody kind of working together and really helping this balloon get up.
After much preparation, we were able to do our first balloon launch. And although it was our first one and we heavily prepared, we obviously had a lot of challenges. The balloon was unable to successfully fly up, and it was sort of levitating on the ground. This led, which you can see on the graphs, just slight amplitudes between the pressure, between the altitude and the temperature. But this was a very good learning experience that we were able to apply for our next launch.
With our second balloon launch, we were able to fix many of our problems from the first try, and the balloon eventually was able to launch. We added another balloon, we reduced the weight, and it actually lifted off the ground. And while the balloon did begin to lift and even gained over 21 feet of elevation, unfortunately, one of the balloons actually popped due to the hot heat outside in the Texas weather, and that ended this attempt. As you can tell from the graphs, where it says balloon popped here, the altitude goes up and the pressure goes down, as that's a correlation, and then it very dramatically falls.
Our third launch was the most successful, with an altitude of over 75 feet, although it did not meet our goal due to the lack of balloon lift. Despite that, we received accurate and meaningful data that shows the connection between conditions and altitude. As we've seen in the graph, we see how the data was corrupted by winds as they pushed the balloon into the tree, as shown in the data.
Some of the challenges we faced during this project include the interconnection between all of the cameras, the microcontrollers, and the sensors, and the specific coding needed to power those sensors and take accurate data. Not only that, we were restricted to working on site because of the limited equipment that we were able to take home.
Also, with our launch, we had a couple of issues, being that, one, our payload weight required 6 balloons. It required a lot more than we actually expected. There's a lot of specific coding needed to go in place. There was a lot of wind. As you can see in the image, the balloons are flying horizontally, which led to our launch not actually going up very nicely as we thought. Heat, which led to some balloons popping, and overall, we did have some challenges, but we were able to overcome them and successfully gather some data.
Not only this, our entire project was made from scratch, and so all of the things we encountered, we had to encounter starting from the ground up.
All in all, we collaborated and assembled a high-altitude balloon to monitor atmospheric conditions during balloon launch. We also retrieved accurate data and analyzed to support our hypothesis.
We learned more in depth on the functions and capabilities of the Raspberry Pi and its coding, and we supported our own vitality of leadership, initiation, and collaboration.
In terms of future studies, Professor Nokes continues this project with his college students in order to analyze additional atmospheric data, assemble ground station and live data broadcasting, and use our payload to conduct extensive research.
So essentially what's going to happen is our progress that we've made, we're going to hand it off to Professor Nokes, and with his class, they're going to make the ground station and a couple of other things to make it so we can live stream the data from the balloon down to the ground station. Because right now what we do is we have our micro SD card and we have to manually read the data.
Hello, I'm Alexander Boeckmann, and I would like to major in mechanical engineering with a concentration in aerospace, and NASA SEES has really inspired me by giving me an opportunity to have practical research.
I'm Brochu, and my career interests are mechanical engineering with a specialized research in aerospace engineering. The SEES internship has equipped me with valuable research and knowledge that will take me one step closer to my dream of becoming an astronaut.
I'm Briant DeJesus, and I aspire to be a mechanical engineer with a concentration in aerospace engineering. In terms of how the NASA SEES internship has impacted me, well, it's exposed me to an ideal engineering environment where I can actively participate in meaningful research. In addition, it provided me with a sophisticated outlook on what it means to be innovative.
Hi, I'm Jorge Hernandez, and I'm interested in being an engineer but also a scientist. And this NASA SEES internship has really inspired me by meeting all these professionals and fellow peers.
That was great.
My career interests are aerospace engineering, environmental science, linguistics, and international relations. The NASA SEES internship program has impacted me greatly. It has inspired me to see myself in high positions within STEM by challenging me to be a better researcher and a teammate, by putting me in advanced scenarios with a high standard. It has also given me an opportunity to represent the first generation community.
Hello, my name is Reveles. I dream to be an aerospace engineer and hopefully one day be able to design spacecraft and lunar bases. SEES has taught me the importance of building networks and take initiative, and also be a leader and persevere.
Hello, my name is Schaeffer, and I want to be a mechanical or aerospace engineer. The SEES internship has really impacted me because it's helped me hone in on aerospace engineering specifically, because before I didn't know what type of engineering I wanted to do.
I'm Sinha, and I want to go into mechanical aerospace engineering. How has the SEES internship affected me? It solidified my passion for aerospace and showed me that it's a real possibility in my future.
We wanted to give a special thanks to remote sensing scientist James T. Dietrich, aka Pi Guy, CSR Senior System Administrator Jim Pollard, aka IT Guy,
And the Eclipse team would be remiss if we didn't give a special thanks to Thomas Quattro Hanover.
For making our NASA SEES experience just as fun as it was academically empowering.
Thanks,
you.
Quattro.
We can't forget about our favorite high school senior peer mentor, Anchal Sabe. We are the NASA SEES Payload Eclipse project, and thank you for watching our presentation.